2 is 6/100.
Yeah, and you have to use your answer from 6.99, but you
Oh.
don't have to do 6.99. So
Yeah, you just kind of had to go through that one.
yeah, and I can figure out 6.99.
Oh, okay. Right. So in this case, there was the blood pressure. What studying whether somebody's hypertensive, right? It's classified as hypertensive if on any one day, if the systolic blood pressure greater than or equal to 140, or diastolic blood pressure greater than or equal to, what do they say, 90. And so up above, there's 10 days. And so if you look through the pairs of values, right, you can count the number of times that it exceeds one of those, the number of days on which it exceeds one of those. So I don't think it ever gets above 140. So this person never crosses that. But there are a few times above 90. There's like 1, 2, 3. So it's greater than or equal to 90. So there's 1, 2, 3, 4 times. The diastolic blood pressure greater than or equal to 90. So I guess p hat is going to be the 4 out of 10, or 0.4 as 40% for doing that, right? And then, it'd be classified as hypertensive if the probability on an individual day is greater than 20%. So if we have 40% in this sample, make a confidence interval for that and see if it compares to 0.2. Now, one aspect about this problem is, so the confidence interval, p hat plus or minus, with 95% confidence interval, is that z-value, p hat 1 minus p hat over n. Right? So one aspect of this is that we really use the, I'm sorry that it wasn't it could be an assign, everybody can kind of do it, so to get that number. But if you feel free to ask questions or send emails about details and things like that, because I can often respond, and even if it's at kind of in the evenings or mornings or something like that. I don't not on all the time, but periodically. And sometimes people ask, more than one student asks a question. Usually I get the same kind of set of questions on key things. So, but anyway, this is a pretty small sample size to really be using normal. And so the book actually gives some things called exact methods that actually look at binomial probabilities and figure out what is the lowest probabilities that can reasonably have been produced 0.4, or the highest probability that have reasonably could have produced 4 out of 10. And so there's some exact methods that would be a little bit better in this case because the sample size is pretty small. But in this case, if you use that as a confidence interval, that would be fine. That's the formula we've used so far. But any other questions on just kind of getting that one going? And so the fourth one was 7.60. And so on. So that looks like it's about the relationship between a hypothesis. Well, those are always at the end of 7. Relationship between a hypothesis test and a confidence interval, right? And so we'll talk a little bit more about that. We talked a little bit about that before, right? But and it's relevant to what we'll kind of emphasize today. But there's a duality between the confidence intervals and hypothesis tests. It's really kind of telling us some of the same information. Right? We're really asking the question, what are the values of that parameter? What's the proportion? What's the mean? What is it in the population? Right? And the confidence interval shows us, well, here's this interval, it's probably in that interval. Right? We're 95% confident that the interval actually covers the true value. The hypothesis test, we said, could it be that value? Right? And if it's in the interval, it's not going to be rejected. But if it's outside of the interval, we typically do reject it. So this one, test the hypothesis, the high fiber diet has an effect on cholesterol levels compared with baseline. Right, so if you do the, so this one, right, high fiber versus baseline, down there, it gives a confidence high fiber baseline, right, it gives an estimate at negative 14, and it gives an interval that's negative 21 to negative 7. So if you take, and so the outcome they're looking at is cholesterol. So if you take high fiber minus baseline, and it's negative, right, that means that baseline's bigger. So you're subtracting something, forcing it to be difference being negative. And so in hypothesis testing like this, we're often interested in, is it zero? Is it in null hypothesis? No difference. There's no difference in cholesterol based on these diets. But in this case, is zero reasonable? The confidence interval's all negative in terms of milligrams. This units are milligrams per deciliter for cholesterol. So if we had tested that these things are equal, this is unequal, and the equal means that the cholesterol, the average for high fiber equals the average for baseline, would mean that the difference would be 0. This interval, this 95% interval, doesn't cover that. 0 is not there. So based on that, we would reject. And if we do 95% confidence, there's a 5% chance we'll miss. If there's a 5% significance level, there's a 5% we'll make the wrong decision if the null is true. So that 95%, 5% matches up in terms of the likely errors. And we reject with small p-values. So the p-value has to be small. So p-value must be p-value. Should be less than 0.05. And we would reject the null hypothesis in this case. So. And then the next two parts have you look at the other ones. Right? Particularly looking at high fiber versus low fiber, the interval goes from -8 to +7. It straddles 0. So maybe it is 0. You can't reject 0 in that case. The others, there seem to be doing either low high fiber or high fiber diet seems better than baseline. But there's not a significant difference between those two types of diets. But any other questions on the homeworks or? Yeah.
5.
So homework 7, number 5, 796. And there's some art output that's given on the next page about this, right? So this one was a little bit kind of the statement of figuring out how to do this. It was a little bit complicated what the measurements were, right? And so there was a baseline measurement and a measurement immediately after the treatment, and then after 5 minutes, and after 10 minutes. But each of those things was really an average of two readings at each period of time. So that's why the first part of the code does the averaging. And then it does a t-test. And so if we go to our assignments, and on our 7th one, so this one had a little bit of computer output on it down here at there it is. Where is it? Oh, it's down here. There it is. So there was this tiering, right? Baseline, immediately after, and each of those really were an average. But to figure that out, you had to read, I had to read the document they had explaining what the variables were and try to figure out Amen. But then the result of doing a t-test goes like this. Right? So in a computer, the TPU1 and TPU0 is baseline and immediately after. There's measurements on actually 14 individuals in there at 2 time periods. And so the change, we take the difference of each one. And it does a test. And so if there's no effect, then the average is 0. So data, that's the data. The alternative, the true difference, it means it's not equal to 0. The alternative is that it is 0. A 95% confidence interval for the difference. Change from one time to other is 4.8 up to 9.7. And so is there an average change in the response baseline versus immediately after from this treatment? Well, this would suggest that there is some change. So this measurement of these things, right, is positive 7.2 on that scale. The interval's all positive, so there's not a 0 change, right? There's not a 0 there. It's fairly far from 0. So the t statistic that comes out of this, right, is this 6.4 is a fairly big t statistic. Right? Usually we compare that to about 2. Right? If it's bigger than 2, it's usually significant. Right? With smaller degrees of freedom, you might need to be a little bit bigger than that, but 6 is just way out there. Confidence interval is not close to 0, and the p-value represented by this is very, very small. Once it gets to be real small numbers, they use scientific notation to represent that many zeros. So that e to the negative 0.5 really means 1, 2, 3, 4, the 5th position here, 4 zeros, and then a number, five places to the left of the decimal. And so that's quite small. And so certainly it would be less than 0.05 or other smaller standards. So it would be highly significant. There really is a difference there from that algorithm. The other ones, ask, the next 3 really use this output, right? And so there's going to be a t statistic for each one, p-values, confidence intervals that are associated with there. And it looks like really in all cases here, it's kind of the same thing in terms of just general significance. Is it significant or not? None of them include 0. There's a difference as you go from baseline to right afterward to 5 minutes to 10 minutes and so on. The average measurements are all changing, significantly changing, and it's nothing staying the same. Other treatments might have kind of a big effect at first and it might flatten out or something. And this is saying that no, it just keeps changing. Keeps having that effect. But that was reading some of the things from that and using that to interpret. This is also relevant to kind of interpreting hypothesis tests because you get the output, sometimes it's a confidence interval, t-value, p-value. What do you look at? And how do you set up the hypothesis becomes a challenge in an applied problem. But any other questions about? So if you've handed in the homework and want to add a little bit to those, I'll be around, a little bit later, so we could add those in and for those parts. So let's look at one example, and we'll talk about some of these issues as well. So here's an example that we can do, right? So breastfeeding generally is recommended for infants in terms of all the health benefits, nutrition benefits that it gives. But there's a question of how long should that go on. Are breastfed infants iron deficient? At 6 months. Right, so that's our main research question. Babies, when they're born, actually have stored up iron from their mother's system. And so they start out with these iron reserves that helps them make blood and helps them grow. But as they get bigger, they deplete that reserve and have to take it from their food environment. Right? And breast milk is high in iron, but is it high enough? Right? So let's say we had 26 infants, right, at 6 months who are not otherwise getting formula or other supplements, right? And we measure for them iron in hemoglobin. And this was measured in grams per 100 milliliters of blood. And the standard deviation is 3 grams per 100 milliliters. And the average is 12.9. And, doctors, physicians could have created a standard where, goal is about 13 grams per 100 milliliters. And so maybe they can get that 13 grams of iron per 100 milliliters with babies that are supplemented, that take formula, that they can be enriched to produce that. Are these 26 infants evidence that infants that are breastfed that at 6 months are iron deficient? So there's 2 ways we can answer this question based on what we know so far. We can do a hypothesis test, or we can do a confidence interval. So which one do you want to look at first? Hypothesis test or confidence? Which one does one seem more natural to you versus the other one? Confidence interval. So let's do a confidence interval, right? So with these quantitative data, and this, our formula for our confidence interval is going to be x bar plus or minus reduce a t, and then do standard error s over the square root of n. So we need degrees of freedom. We need to know which t distribution to use. Right? So it's n minus 1. So there's 25. So it's 26 minus 1 is 25. Right? So we want to look up, let's do a 95% confidence interval. 95% is fine. The t-value that cuts off the upper 2.5% that we would use for this with 25 degrees of freedom is 2.06. Let's see. I think that's a t-table that's there for the power thing. You can look that up with the t-table. So this is Rosner's version of his t-table. Right, so if we go down here to 25, we're going to look across this 25 row here. Right, and we look under this 0.975 column. I wrote 0.025. Different books will use either the upper 0.025, or 1 minus that is 0.975, but it would be this value here, right, and 2.06. Right, is that cutoff value, right? So that's where, so this 25, we're getting this value here for that one. And so we're going to take our x bar 12.9 plus or minus 2.06. And then s was 3 over the square root of 26. And that interval looks like 11.9 up to 14.21 grams per 100 milliliters. What do you think? Is 13 reasonable?
Feels like it's almost in the middle.
It's about in the middle, yeah, it's pretty close. So, right, it's about in the middle. 13 seems pretty reasonable. So, 13 is in the interval. No evidence, really, in this case, of iron deficiency. On average, on these infants, 26, they came out pretty close to 13, and so no problem. What if, instead, we had had not 12.9, but we had 11.4. Again is 26 again. X bar, instead we had gotten 11.4 grams per 100 milliliters, and the standard deviation was still 3. What would happen then? Well, we follow the same procedure for a confidence interval. X bar plus or minus the 2.06, right, S over the square root of n now is 11.4 plus or minus 2.06 times the 3 over 26. And that was set up, it's 1.5 lower. So 1.5 lower. Let's just put it on the computer real quick. I don't rely on doing the math in my head. Get rid of this thing, close that up. I'll just start a basic R thing up here without the RStudio for now. Make it a little bigger. Right, so if it was 11.4 minus 2.06 times 3 over the square root of 26, it goes down that far. But if it's plus, right, it goes 10.2 up to 12.6. That's an interval. 10.2 up to 12.6 grams per 100 milliliters. If that had been the interval, based on our sample, what are we going to think about these infants now in iron deficiency? Yeah, now there's evidence that there's iron possible. Now, with this sample, there is evidence of iron deficiency on average. So that would suggest that, if that really held up in larger studies across broad populations, that would suggest some warning. It's fine to keep breastfeeding, but for iron's sake, at least for that nutrient, supplementing, starting to introduce some type of foods that would have, oatmeal or something that they can handle at a young age, that they can digest, that would have added iron to boost that and avoid it. Maybe having the mother take an iron supplement would have it, be beneficial. But in any case, if that were the data, then the confidence interval will shift, and we would think differently about 13. The other way that should be equivalent in terms of giving us information would be a test. So if we tested, is the mean 13 grams per 100 milliliters versus not, it's not equal to that. And maybe we would do one-sided if we're concerned about it being lower, but for now, let's just think about the two-sided. We have two scenarios. N equals 26, S equals 3 for both 1, but X bar is 12.9 and 1. The other scenario has the same things going on here, but X bar equals 11.4. based on know what the confidence intervals, we did the two-sided things. What can you tell me about the p-values? The p-values, in which case is the p-value going to be less than 0.05? In which case is the p-value going to be bigger than 0.05? Well, let's look at the t statistics. For testing this, we took the x bar minus the null hypothesis value, and then standard error, S over the square root of n. So 12.9 minus 13, 3 divided by the square root of 26. Over here, this one, the t statistic. I like to write statistic under this, because we also have a t distribution, and this is the value actually computed from the data. So that's the statistic value is statistic 11.4 minus 13, 3 over the square root of 26. This statistic value over here, right, we don't expect it to be too extreme, because 12.9 is pretty close. We didn't reject, and actually it's negative 0.17. Almost at 0. Right, because it's almost there. I'm not sure what the other one is exactly. So if we do this other one and do 11.4 minus 13 divided by 13 divided by the square root of 26. Is that right? How did it get 11.4? 13. What did I? Oh, 3. Sorry. Negative 2.72. So I knew it was wrong because I knew we had to reject. We had to get a small value. And so negative 2.72. Negative 2.72. Right, so we compare those statistics to the critical values from the t distribution. How far away is typical? And what's kind of the limits of what's possible? So n is 26 degrees of freedom, n minus 1, that t 0.975 in Rosner's book for 25, and it was 2.06. So because this one is, negative 2.06 is less than negative 0.17 is less than 2.06, because it's in the middle, right? We don't reject. But that other one is below the lower endpoint, right? So it's more standard errors away. Here, negative 2.72 is less than 2.06. This is the t statistic value. This is the t25 value with the 0.975 on it. Over here, we do reject. We do think it's not equal to that, and it would be lower. Any questions about? So two little wrinkles, right? So what affects this? What affects these? Well, obviously the changing the mean affects that, right? If the mean's further away, you get more significance. You get t-values that are more extreme. So besides x bar, what affects the confidence intervals and hypothesis? What would make our results more significant? Of course, as we just talked about, if x bar is further away, right, then there's a bigger difference, and that's more significant. But what else? We can look at the confidence interval formula, right? There's our x bar plus a t value, right? S over the square root of n, so both s and square root of n, right? So bigger sample size, you're dividing by a bigger number, and it's narrower. bigger n, confidence interval is narrower. So say we had 260. Right. Well, a t 0.975 with, we do the different degrees of freedom, that's about 1.99. It's 1.97 or something like that. It's not much different from a normal. It's pretty close to 1.96. But we would, with a half size here, would be about 1.97. So that'll be smaller. And then we'll have s over the square root of 260. So it'll be quite a bit smaller. It's possible, right? Even if you have this difference of 12.9 versus 13, you might make an interval that doesn't include 13, right? If we had 26,000 infants, right, you can get these little tiny intervals. N equals 26,000. Infants, a big study, 12.9 plus or minus, well, that's going to be almost 1.96. And if it was 3 as before, 26,000 here, we can see what actually happens with this thing, right? I calculate it. Well, so I'll do 12.9 plus, what is that? The QT, the normal quantile that I want, actually with the 26,000 minus 1 degree of freedom is about 1, it is practically 1.96. So 26,000, it's almost indistinguishable from a normal. So if I did 12.9 plus 1.96 times 3 divided by the square root of 26,000, it doesn't get up to 13. The negative of that, the lower endpoint would be 12.86. Right? So from 12.9 with 26,000 infants, I'm going to reject 13 and think it's lower. Right? So this one does not include. This would be about 1.96 with that number. So 13 doesn't look reasonable. Is that so? It's statistically significant. Right? We would reject 13 in a hypothesis test. Is it practically important though? 13 grams versus 12.9 grams. Right? That's really medical discipline. Is that really going to impact development to be 1/10 of a gram lower on average? Right? So there's a difference between. So in this case, that type of difference, there is statistical significance. But is there practical, kind of real world, right, health significance? And that's really a medical question, right? You might measure that in how the babies develop over the next 3 months or next year or 2 years or something. But big enough sample size, you can basically prove almost anything is statistically significant because it's unlikely to deviate from its actual mean very much. But it might not really want you to change clinical practice. It might not decide that they need supplementation, or to say, or to criticize breastfeeding on this grounds if there's such a small difference. Now, if it was the other case where it's 11.4, well, 11.4 versus, that's a more than 10% difference, right? Reduction in iron, so maybe that's medically significant. So the N affects it, right? Now, the other thing that affects it is that S. So I'll say smaller sigma because you don't really get you might get a smaller standard deviation in the sample just by chance, but If we would do something different, maybe we would get smaller standard deviations overall. So standard S, that sigma, maybe this is a measurement issue, right? You send a sample out to a lab and they measure it. You send it to them again, they measure it, and there's a big difference. Right? That's measurement error. If you can reduce measurement error by giving a more precise measurement, S might go from 3 down to 2.5. Right? So if you can reduce it, right? So if you reduce measurement error, you might reduce that. The other possibility is to take a more homogeneous sample or study a more homogeneous population. So in studying infants, how do you select a group, or how do you define your research question around a group that's more homogeneous and has less variability? Well, maybe restrict it to term babies, so babies that were born at term and started at full size. Maybe you start ones that were born in a certain weight range. Right? You do ones that were a certain length to begin with, right? And so you pick infants that are less variable. And then you know something about the mother's diets, right? You don't necessarily know that they're supplementing with iron or something, but that they're just eating kind of a certain types of diets. So kind of either one of these things could lead to smaller standard deviations, right? So suppose we reduced measurement error or choose a smaller group and get an S of 2.5. If everything else is equal to 12.9 and N of our 26, we're still going to use degrees of freedom equals 25. So our T value for 95% confidence interval is going to be 2.06. So if in this case, with this smaller standard deviation, right, then X bar plus or minus RT S of the squared of N is narrower. It's probably not narrow enough to exclude 13, right? But it's smaller. I'll put 2.5 in red here to show the difference here. And so it's just going to the smaller standard deviation if it works out that way, or if we can plan it to reduce uncertainty and error, you might get that. So one of these up here. This one, 3, if this was 2.5, and this was the 12.9 again, we get that as a lower limit, or as an upper limit, 11.89, 13.91. That's a little narrower. Before we went above 14, 11.89, and then 13.91. Narrower, more narrower than the original. So it wasn't quite enough to move it down to 13. 13 still is very plausible, but it's had an effect. Right? So if you're doing a study and planning it and you control the measurement process to reduce that, it's worth doing. If you're going to spend $10 million on a study and you can control one of the measurements that on a key outcome that's going to make it less variable, it's worth doing. But any questions about it? So one topic we want to talk about is, what is alpha? We usually let alpha equal 0.05 or something like that. So it's alpha that's significant. It's also called the significance level. So this is a probability that we reject the null hypothesis if the null hypothesis is true. We usually draw this picture right here is here's the sampling distribution of X bar. And if we get an X bar that's extreme, we reject. How do we determine that? Well, we look at the, out here is the rejection region on the positive side, and here's the rejection on the low side. And this is the sampling distribution of X bar, so X bar falls somewhere on here, right? But how do we determine that, right? We set it up so that if we really are supposed to be here, and this is really the sampling distribution, and most of the time we're going to be close by, sometimes we get an extreme value, right? 5%, so 2.5% out here, 2.5% out here. The alphas tell us that to make it that percentage out on the edges. Right? Just like a confidence interval, about 5% we miss, about 2.5% of the time we miss high, 2.5% we miss low. It's because we're getting an X bar that's unusual. 2.5% of the time it's high, 2.5% is low. That's just the way it works out. Right. That's an error assuming the null hypothesis is true. What if the alternative is true? Right. The alternative is true. We are not, our reality is not the null hypothesis anymore. So here's mu sub 0. What if it really is some alternative out here? What if that's really the truth? Right? Then we do want to reject. Right? Rejecting is a good thing. Rejecting the null hypothesis in favor of something that's different. Right? And we do want to reject. If H0 is false, and the alternative HA is correct, then we do want to reject. The null hypothesis and conclude that the things have changed and things are different, things are better or worse depending on how we're phrasing things, right? And so there's a corresponding error rate or probability associated with doing that, with getting the correct decision if the alternative is true. Right? And that's called power. So statistical power is the probability that we reject H0 if the alternative is true. And this isn't called, it's given a symbol to. Beta is 1 minus that, or power is 1 minus beta. And beta is the probability we fail to reject if H0 is false. So beta is the probability it is failed to reject if HA is true. Right? And so most studies that get done at large centers or large research questions consider, they set an alpha level like 0.05. It's kind of a decision you make up front, right? And then they look at what they know about the scientific problem. What are the differences between the treatment and the control group? What they think it's going to be. Is it going to be 5 milligrams? Is it going to be 1 milligram? Whatever units you're dealing in. How big is the difference going to be based on what they anticipate? And then they ask, what's the probability we're going to get a significant result if our alternative is really true? And if it's not 80 or 90%, it's probably not worth doing a $10 million study. So they do consider it as power. And power on the hand is described on the handout. So we have a copy of that, which everybody has on there. Right? And so in terms of this power, a statistical test. So I say kind of limited here. We're kind of do a limited take on this. We're not going to fully use all the formulas for calculating power and sample size. They get a little more involved, and then on a second level course, you probably would do that in an applied area course, and continuing into Master's of Public Health or something like that, or Masters in other biology would do this. But let's say that you're considering a couple hypotheses. For now, let's assume that the sigma is known, so just to simplify things and use normal. Right? We reject the null hypothesis if our statistic is big enough. Right? If it's bigger than mu plus a few standard errors, or less than mu minus a few standard errors. Right? That's where we reject. Right? That's essentially all determined by the null hypothesis. And the alternate being decided. But if the HA is true, right, we can calculate the probability that we do reject. Right? So power is illustrated by the shaded in area here. So if the null hypothesis is true, we reject the null hypothesis, right? If it's up here or bigger. Right? So if X bar is away from the sampling distribution of X bar here. So if X bar is really low or really high, we reject. But if this is the reality, if that's really where the center is, right? Well, then we have a normal curve over that center, and you can calculate the probability you're in one of those areas under there, and that's power. You want that to be big. This one on this left is almost 0, and most of the power is up here. This would be an okay picture, right? Because what do you think the probability is that we're up here in this tail, or that we're in this rejection region up here under this alternative? What does that area kind of look like to you? I know you're not going to get it exactly, but is it more than 50%? Yeah. So 50% would be right here at the middle, right? If the rejection region started here at the alternative mean and went up, we'd have 50% chance to be 50% of the curve, right? But it's a little bit more, right? 60, 70, 80 maybe, right? That's what we want. So here's a little numerical example on this one. Say that, for a car like the Honda Civic, the EPA does a bunch of tests and says that this car gets 36 miles per gallon on average. And there's a standard deviation of about 6.5 for individual cars, individual drivers. And then you go out and measure 50, and you get a standard deviation of 6.4. The standard deviation is 38.3. That's an 8. Well, do we reject the null hypothesis? It turns out that we would. Let me see if I can get it to change color with the mouse. We could just look at when do we reject? Taking the 36 minus, we're pretending we know sigma in this case, we're using a normal. We would reject if we're less than 34 or greater than 37. Now, if we actually got 38.3, we would in fact reject and say, go to the EPA and say, look, we did these tests, our car is better. You got to raise this for us. You're underselling us. We want to sell more cars, so you're not giving us the credit we were due. We are significantly better. Right? But power is kind of a planning issue. If we really thought it was 38.3, what would be the chance we would reject? What's the chance if we tested 50 cars, we would get something above 37.8? It's going to be on that side because it's bigger. So the chance we're less than 34.2 or greater than 30.8, you add those two together, that gets power. The first one is almost 0. That's that little tiny tail way to the left on the wrong side, so that's not going to happen. But the chance that you're greater than 37.8 when it's actually 38.3, when you z-score that, you get the chance that a z is greater than negative 0.54, and that's about 0.7054. We're about 71%, so power is almost 71%. The chance you don't reject is about 30%. So it's better than 50-50, but it's just still not super. And you can do these things where instead of having 50 cars, we can say, what's the power if we had 70 cars? Right? Well, then the standard error changes. We reject for a narrower range. Right? And the chance we're above this other one ends up being about 84%. So if we could say, look, we need 70 cars instead of 50 to get a better chance of getting a significant result. Let's not do this study. Let's not go cheap, because there's a chance that we're going to fail. Let's expend the money, justify the bigger budget, right? And get a better chance of getting a significant result. Right? So sometimes, 84% of the time, if that if this 38.3 is accurate, and the standard deviation is accurate and stuff like that, then you're likely to get a significant result. You can go to the EPA and say, look, our cover is better than you're saying. Here's the result. The 70%, the sample size of 70 with 84% power, you can kind of use to justify it and give a rationale for doing the study. So sometimes you get insignificant result, like that blood pressure, like the iron in the blood one. It's based on 26. Maybe that's too small. There's very, very little power. Even if it was 12 versus 13, it's probably still pretty small power to do that. You could do a power calculation and say, we need 50, we need 100 to make this reasonable. So sometimes with hypothesis tests, you don't reject. But that doesn't mean the null hypothesis is true. Sometimes you don't reject because you have a really big standard error, based on a small sample size. So anyway, that's power. Mostly we're going to talk about qualitatively what you need to be successful with a hypothesis test or a confidence interval. You need adequate sample size to do it. It affects the width, it affects the significance, and it affects the signal power. So. All right. Well, have a nice break. See you afterwards. And if anybody else has homework.
Yeah. See how it's up there and goes back home.
Yeah.
I was just trying to plan ahead. When would homework due?
Probably the Friday after the event,
Okay.
because Monday will do a little bit of review and a little bit of new work.
Okay.
But I think Friday. I think it's posted now even.
Okay.
So you can get started on it.
Thank you.
Enjoy your break, Professor.
Thank you.
Have a good one.
You too.
Thank you.
Thank
Have a
you.
nice break.
You have any military service over the break?
Yes.
You do?
Unfortunately. I mean, we're getting ready to go to Guatemala, so they really upped the training.
Yeah.
But
What are you going to do in Guatemala?
we're building a school and a hospital, so I'm excited for that. Next month we have the gas chamber that we got to go through again,
Oh,
and a lot of like weapons qualifications. But it's like not. I don't think.
gas chambers for exposure to
Exposure
like
to the-
practice exposure.
Uh-huh.
Being able to function while the rest of the world's incapacitated.
Yep. So.
Well, that's a unique experience. So.
Oh, definitely. But yeah, have a good break.
Yep, you too.
See you soon.